conductance with dilution. There is specific conductance with the dilution. It is variation of specific conductance. Variation of specific conductance. Specific conductance with the dilution. Variation of specific conductance with the dilution. What do you mean by specific conductance? That is the conductance offered by unit volume of the solution. That is 1 cubic centimeter volume of the solution or 1 cubic meter volume of the solution is called specific conductance of the solution. Now what happens when dilution increases? Means when you are going to add more and more quantity of the solvent like water, then what happens? The number of ions per unit volume that decreases, because the ions will spread out and the ions which holds in 1 cubic centimeter volume of the solution or 1 cubic meter volume of the solution will be lesser one. Therefore, since the conductance that depends upon the charged particles or ions, since the amount of the ions in unit volume decreases and hence the specific conductance decreases. Therefore, the specific conductance of a solution decreases with increase in dilution. Specific conductance of a solution decreases with increase in dilution. Now, during dilution of a solution by adding water, during dilution of a solution by adding water, by adding water comma, the ions are spread out. The ions spread out. Number of ions present in unit volume, number of ions present in unit volume, number of ions present in unit volume decreases, becomes less. Becomes less. Hence, specific conductance decreases. Hence, specific conductance decreases with increase in dilution. Specific conductance decreases with increase in dilution. Variation of molar conductance with solution. Next, variation of molar conductance with the solution. Next one, variation of molar conductance with solution. Variation of variation of molar conductance with the solution. Conductance of solution depends upon conductance of a solution depends upon conductance of a solution conductance of a solution depends upon nature of the ions, number of ions and velocity of the ions. Number of ions, number of ions, and velocity of ions. Number of ions and velocity of the ions. In case of weak electrolytes, for weak electrolytes, For weak electrolytes, the degree of dissociation or degree of ionization increases. Therefore, the number of charged particles or the number of ions present in the solution will be increases, and hence it depends upon the number of charged particles. Therefore, the conductance increases with increase in dilution. In case of weak electrolytes, the degree of dissociation of the electrolyte increases. When the degree of dissociation or degree of ionization increases with the dilution, then the number of the charged particles present also increases, since the conductance that depends upon the number of the charged particles, and hence the conductance value increases. Degree of dissociation of weak electrolyte increases with dilution. Degree of ionization or dissociation, increases with increase in dilution. Increases with increase in dilution. And hence number of ions increases. Since the conductance depends upon the number of ions, hence the number of ions increases. Since the conductance depends upon the number of ions, since the conductance depends upon number of ions, number of ions, and hence conductance increases. For weak electrolytes, degree of dissociation increases, and hence the number of ions increases, therefore the conductance increases. Degree of ionization or degree of dissociation increases with increase in dilution. This implies that more and more amount of the undissociated molecules will undergo ionization reaction. Hence the number of charged particles or ions increases, since conductance depends on number of ions, and hence the conductance value also increases. This is in case of the weak electrolytes. In case of strong electrolytes, in case of strong electrolytes. In case of strong electrolytes. Strong electrolytes. For strong electrolytes. For strong electrolytes, even at higher concentration of the solution, we have fairly the sufficient number of the ions and hence with a definite conductance even at undissociated state, because even in concentrated condition the strong electrolyte contains some quantity of the ions, since it depends upon the conductivity depends upon the number of the ions and hence the number of conductance is more. Whenever water is added, then the intrionic force of attraction between the two kinds of the charges that decreases, therefore the velocity of the ions increases, therefore the conductance increases. See, in case of the weak electrolytes, the number of ions increases. In case of the strong electrolyte, velocity of the ions increases by the addition of the water, since electrostatic force of attraction that decreases, therefore the conductance also increases. Okay. A strong electrolyte remains completely ionized. A strong electrolyte remains completely ionized. A strong electrolyte remains completely ionized. Completely ionized. Completely ionized even at higher concentration. Completely ionized even in the fairly concentrated solution. Even in the fairly concentrated solution. Fairly concentrated solution. Fairly concentrated solution. Fairly concentrated solution. Upon dilution, hence some ions exist as ion pairs. 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 Some ion pairs. Ion pairs which are not available for conductance. Which are not available for conduction. 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 Ion pairs which are not available for conduction. Which are not available for conduction. Upon dilution, these pairs dissociates to produce. Upon dilution, these pairs, these ion pairs undergoes ionization. These ion pairs undergoes ionization and electrostatic force of attraction. Electrostatic force of attraction, electrostatic force of attraction decreases, electrostatic force of attraction decreases, migration or velocity of the ions increases, velocity of the ions, velocity of the ions, and number of ions increases, and number of ions increases, velocity of the ions and number of ions increases, conductance increases, conductance increases, conductance also increases. This is about the strong electrolytes. This is about the strong electrolyte. Moreover, velocity of the ions increases upon dilution. Hence, lambda increases upon dilution for strong electrolyte. Therefore, molar conductance of the solution, therefore, molar conductance of solution, therefore molar conductance of solution increases with dilution, increases with dilution. Whether it is a strong electrolyte or a weak electrolyte, anyhow the molar conductance of the solution that increases and acquires maximum value at infinite dilution. This law is called as a Coleridge's law. This law is called as a Coleridge's law. The molar conductance of any electrolyte, whether it is strong or weak electrolyte, increases upon dilution. Increases upon dilution. The molar conductance of a solution, the molar conductance of a solution of any electrolyte either strong or weak electrolyte, strong or weak, increases with increase in dilution, increases with increase in dilution, increases with increase in dilution. Therefore, molar conductance of a solution that increases with increase in dilution, increases with increase in dilution, increases with increase in dilution. It reaches limiting value. It reaches limiting value at infinite dilution. It reaches limiting value at infinite dilution. Infinite dilution means when more quantity of the water is added, then the conductance further increases. The limiting value of molar conductance is the limiting value of the molar conductance. The limiting value of the limiting value of the molar conductance is represented by represented by lambda m naught, lambda m naught, lambda m naught. 0 indicates zero concentration, 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 zero concentration. It is called molar conductance at infinite dilution. It is called molar conductance at infinite dilution. It is called molar conductance at infinite dilution. Molar conductance infinite dilution. Infinite dilution. The molar conductance of any electrolyte, either it is a strong or weak electrolyte, that increases with increasing dilution, it reaches a limiting value. It reaches limiting value at infinite dilution. The limiting value of the molar conductance is represented by lambda naught m. 0 indicates the zero concentration. It is called molar conductance at infinite dilution. It is called molar conductance at infinite dilution. Molar conductance at infinite dilution. Lambda m is related to concentration. Lambda m is related to concentration. Molar conductance is related to molar concentration. Molar conductance is related to molar concentration by using the expression lambda m and concentration. Molar conductance lambda, molar conductance lambda m is related to concentration, in particular this is molar concentration. It is represented by C. Molar concentration is represented by C by using the relation lambda m is equal to lambda naught m minus A into square root of C. Lambda m is equal to lambda naught m minus A into square root of C, where lambda m is equal to molar conductance of the solution. Lambda m is equal to molar conductance of the solution. Lambda naught m is equal to molar conductance at infinite dilution. Molar conductance at infinite dilution. C is equal to concentration of the electrolyte. And A is equal to concentration of electrolyte. A is equal to concentration. A is constant for given electrolyte. A is equal to constant for given electrolyte. Constant for given electrolyte. By plotting this graph, for strong electrolytes, for strong electrolytes you have to plot the graph. This is lambda m and square root of c. Lambda m with the square root of c. Square root of c. For strong electrolyte, it is found to be constant. This is called as a lambda naught m. This is called as a lambda naught m. There is this Siemens square meter per mole. Siemens square meter per mole. That is molar conductance. Square root of the concentration. This is for NaCl. This is for NaCl. This is for NaCl. This is x-axis, the concentration square root, and y-axis molar conductance of the solution. Molar conductance of the solution. This is for strong electrolyte. In case of weak electrolyte, in case of weak electrolyte, a graph lambda m versus concentration is straight line. In the case of strong electrolytes like sodium chloride or potassium chloride, by extrapolating this straight line to zero concentration. Graphical representation of graphical representation of molar concentration versus square root of C is a straight line. Is a straight line. Is a straight line. Is a straight line for NaCl and KCl for strong electrolytes. For strong electrolytes, NaCl and KCl, by extrapolation, by expanding with zero concentration on y-axis give lambda m naught. In an board exam, they will ask you one more question. Draw the plot of the graph of lambda m versus square root of m. In case of weak electrolytes, degree of dissociation increases with increasing dilution. In case of graph is not a straight line in case of the weak electrolytes. Graph is not a straight line in case of the weak electrolytes. Graph is not a straight line in case of weak electrolytes. Graph is not a straight line in case of weak electrolytes, such as acetic acid. What about the this is lambda m in terms of Siemens square meter per mole. here the square root of C. Here the graph is like this. This is for acetic acid. This is for acetic nature. Hence cannot be determined by. Hence cannot be determined by. Hence cannot be determined by. Extrapolation at zeroth concentration. This is separate graphs. That this is for weak electrolyte like formic acid or acetic acid. That is a strong electrolyte in case of sodium chloride and potassium chloride. Sodium chloride or potassium chloride. Next one is Kohl's law of ionic migration. 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 Molar conductance of the solution increases with increase in dilution. Molar conductance of solution. Molar conductance of solution increases with increase in dilution. Increases with increase in dilution. Increases with increase in dilution. Increases with increase in dilution and attains maximum at infinite dilution. And attains maximum at infinite dilution. Maximum at infinite dilution. Maximum at infinite dilution. This is true at a given temperature. This is true at a given temperature. Hence each ion make its own contribution to the total conductance. Hence each ion make its own contribution. Own contribution towards conductance. According to Kohl's law, molar conductance of an electrolyte at infinite dilution is the sum of the contribution of the cation and anion of the electrolyte. And hence, according to Kohl's law, this is very important for one more question. According to Kohl's law, molar conductance of an electrolyte at infinite dilution. Molar conductance of an electrolyte at infinite dilution. at infinite dilation is the sum of the contribution of cations is the sum of the contributions of is the sum of the contribution of the sum of the contribution of the cations, sum of the contribution of the cations and anions of the electrolyte, cations and anions of the electrolyte, anions of the electrolyte, anions of the electrolyte, anions of the electrolyte. Molar conductance of an electrolyte at infinite dilution is the sum of the contribution of the cations and anions of the electrolyte at given temperature, at given condition of the temperature. Therefore, lambda naught m is equal to lambda naught m is equal to lambda of plus lambda naught of minus. This is mathematical form of the Kohl's law. Is the mathematical form of the Kohl's law. Is the mathematical form. Is the mathematical form of the Kohl's law. Mathematical form of the Kohl's law. Mathematical form of the Kohl's law. Where lambda naught plus is the conductance of the cation, lambda naught plus is equal to conductance of the cation, limiting molar conductance of the cation and anion, limiting molar conductance of the cation and anion, limiting molar conductance of the anion, limiting molar conductance of the anion and is equal to limiting molar conductance of the anion. So this is cation. This is cation. Limiting molar conductance of the anion. Limiting molar conductance of the anion. Limiting molar conductance of the cation and limiting molar conductance of the anion. For example, lambda naught of this NaCl is equal to lambda naught of the Na plus lambda naught of the Cl minus, lambda naught of the Cl minus. There is a lambda naught of the NaNO3, lambda naught of the NaNO3 is given as lambda naught of Na plus lambda naught of NO3 minus, lambda naught of NO3 minus lambda. There is a lambda naught of Na2SO4, lambda naught of Na2SO4, lambda naught of Na2SO4 is equal to 2 times of Na plus lambda naught of SO4 2 minus, SO4 2 minus. In general, conductance due to 1 mole of ion of the same kind is called ionic conductance. Conductance due to 1 mole of ions of the same kind is called ionic conductance. conductance due to 1 mole of ions of the same kind. Conductance due to 1 mole of ions of the same kind. Ions of the same kind. Ions of the same kind. This is same kind. Is called ionic conductance. Is called ionic conductance. It's called ionic conductance. Is called ionic conductance. It depends on nature of the ion, concentration of the ion and temperature. It depends upon nature of the ion, and concentration of the ions, concentration of the solution and temperature. Concentration of the solution and temperature. Concentration of the solution. Concentration of the solution. Concentration of the solution and temperature. Concentration of the solution and temperature. What is ionic conductance, and mention the factors that affect the value of the ionic conductance is there. Conductance due to 1 mole of ions. Conductance due to 1 mole of ions of the same kind is called ionic conductance. It depends upon nature of the ion, concentration of the solution and temperature. In general, for AX for an electrolyte AXPY, which produces for an electrolyte AXPY produces X cations and Y anions. Then molar conductance is given by at infinite dilution is given by X into lambda naught A plus Y into lambda naught B plus. A plus and B minus, or plus and minus. It is sufficient. Okay. Next session I will continue the applications of the Colas law and the problems based upon the Colas law. Okay. Thank you.